Hello and welcome to the video lecture review on the JBL book for wireless and mobile device security. This is the second edition. This has been written by Jim Doherty. ISBN number 9781284211726. First of all of the material is copyrighted through JB Learning. They own the rights to all of this. I am just providing video lectures for my classes. I do not represent them. PowerPoints are owned by them solely. All of this is copyrighted through, again, Jones and Bartlett Learning. So for any of that information, reach out to them. This is just a lecture review on their official PowerPoints. Alright, with that said, let's jump right on in. How do wireless LANs work? So that is what Chapter 5 is all about. We are going to be learning about what's a WLAN. Again, WLAN, wireless LAN. We're going to learn about the topologies, the standards, the anatomy, the antennas, and the site surveys that are all involved when dealing with wireless networks and wireless LANs. Alright, so the main question is, well, what's the purpose? Wireless requires access to frequencies. So when we're dealing with a communication channel, normally we'll have a wired connection, copper or fiber. Well, you're attached to that cable. Well, with wireless, we can now send it over frequencies, so you're not having to be attached to something, thus giving you more mobility freedom. So we're going to use ISM, and this is short for the industrial, scientific, and medical bands of the unlicensed wireless spectrum. ISM, again, industrial, scientific, and medical bands of the unlicensed wireless spectrum. So let's unpack that a little bit. Let me grab my pen. Keyword, unlicensed. That means there are licensed spectrums that are out there. Normally, within the U.S., we have the FCC, the Federal Communications... Ooh, too many acronyms today. The Federal Communications Commission. I knew that one. And they are dealing with the licensing of the wireless spectrum within the U.S. So within the U.S. If you go to Canada, FCC is not going to be there. So that means there are spectrums or portions of the wireless network that is okay for people to use, or that are unlicensed. Wireless technologies do require devices have a network to be tuned to specific frequencies within the unlicensed spectrum. Oftentimes when we're talking 802.11, we're dealing with the 2.4 gigahertz or the 5 gigahertz, 2.4 gigahertz or 5 gigahertz spectrum, sometimes the 900 megahertz spectrum, though in a modern wireless network, the 2.4 and 5 are the key ones. So what does this mean? Now, I want you to think about you in the car listening to the radio. You might be listening to 102.7 FM. Well, that should be in megahertz. That's a specific frequency that radio station is broadcasting, so that your receiving radio can actually receive it and process it and allow you to hear what's happening over that specific frequency. So we're going to talk about the frequencies as well as other anatomy of that wireless network as we proceed through this module. Alright, so let's dig into that unlicensed spectrum a little bit more. Remember that the ISM bands are available for short range wireless communication. Your PAN, for example, Bluetooth networks, your wireless LANs, and even some wireless wide area networks. There are some bands set aside for open resources. Again, the ISM does provide access to the wireless spectrum for innovators and product developers through these unlicensed radio frequency bands. Again, they're unlicensed, meaning use at own risk. Also, there are no rules there are rules, there are still guidelines, but for the most part, there are no rules on interfering with one another. They're not as heavily regulated as a licensed band would be. However, devices still have to comply with these strict regulations, and developing products that use the bands do require government approval. Other countries might have their variation. Here we have the International Telecommunications Union, ITU, which will create the standards that specify the frequency bands and the specifics on how to access those bands. The spectrum, power regulations, and other key characteristics are all outlined by these either national or international guidelines based off of your location. Again, most of the spectrum we're fairly familiar with are in that 2.4 gigahertz or the 5 gigahertz. In 2020, we also did get access to the 6 gigahertz band. Let me grab my pen. So again, in 2.4 gigahertz, so let me try to do that again. 2.4 gigahertz band, we're talking wireless. That would be our traditional 802.11, our Bluetooth 802.15. We have things like our RFID, our Zigbee, our 6 low-powered PANs, our NFCs, and things like that. Also, a lot of IoT. I don't know why I did IOI. I meant IoT. Internet of Things also use that 2.4 gigahertz range, while there are growing number of newer devices that are using the 5 gigahertz or 6 gigahertz range. That is a slower process. Again, more popular globally is that 5 gigahertz range. It does have bands of 150 megahertz, so a little bit more than our 20 megahertz bands in 2.4 gigahertz. Does make it suitable for higher data transmission rates. And again, the FCC in 2020 did grant access to that 6 gigahertz bands within the US. What's interesting is the 6 gigahertz band will improve the connection reliability, its speed, its efficiency, also aiding to reduce interference. But like all of our technologies, it will take some time to actually get it to implement. So let's talk about the anatomy. The anatomy is pretty much the structure. So in order for wireless networks to exist, we need two main things. We need first something that will broadcast a wireless signal, some form of access point to our wireless network. Sometimes we call it a WAP, wireless access point. It's typically a wired station that transmits and receives wireless signals. That way we might have a antenna that is connected to a switch where our other machines might be. But what that allows us to do is this connection to the switch provides that connection wirelessly to this LAN. So in this regard, the antenna would be the wireless access point. It's more than just an antenna, but for now, antenna is perfectly acceptable. So that's one of the things you need. Another thing you need is some type of interface card, network interface card. In this case, we're talking about a wireless version, sometimes called a radio card or wireless card or several other variations. Most tablets, smartphones, laptops all have them. You can also do an add-on card. Again, this is going to be an end device or client station that will be transmitting and receiving wireless signals to the access point. The device will have to have this radio card or wireless interface card to actually allow for that communication. These are the basic two items that must be there for basic wireless communication to actually exist. So let's talk about those wireless devices or endpoints or client stations a little bit more in depth. So any device that meets the following criteria is that wireless client. It will contain some form of transmission card, wireless card, radio card, and it is going to be using some form of transmission and receiving, typically denoted TX and RX, transmit TX, receive RX, to handle communication over a wireless or radio frequencies. It does contain some form of antenna. And in this regard, again, wireless client is very subjective. I would not agree with bullet point 3. It operates under some type of wireless protocol? Yes. Operating under specifically 802.11? Maybe not, because 802.11 is our traditional data wireless, not including Bluetooth. So I'd be careful with the 802.11. It's kind of subjective. A client station is also configured to associate with an access point, again, to allow that layer 2 communication to that switch. Again, in the previous slide, we looked at very specifically a access point being attached to a wired network to extend the capabilities of the network through the wireless access point to wireless clients. Some of the things that you're going to need if you are the wireless client, you're going to have to know how to access the identifier of the wireless network. We typically refer to it as an SSID or Service Set Identifier, SSID. This is a configurable name or alphanumeric code that uniquely identifies your wireless network. If there's multiple access points configured with the same SID, and if the correct security credentials are supplied, the client should be handed over to the strongest signal. And that's actually one of the items is the security of that. Again, it goes to the strongest signal. So if there happens to be a wireless appliance there that is more malicious, like a pineapple, for example, then it could lead to some more dangerous items. But anyways, that's more for a security course. Basically, the access points will need to use different channels to avoid any types of interference. Remember, we use channels 1, 6, and 11 when we're talking our 2.4 gigahertz band. That way, there is no interference between one another. Before the client can connect to the access point, you have to find the access point. You have to receive some probes. The client should do this by passively scanning, listening for the probes or beacons, which the access point will continuously emit. When the client can hear it or can see it, can identify the beacon advertising the appropriate SID, then it should, if it's pre-configured to automatically connect, will automatically connect. That's passive. With active scanning, the client will proactively scan the network by sending out its own probe pulse requests. Hey, are you here? Hey, are you here? Hey, are you here? The problem is, with the active scans, on the fly, a Wi-Fi pineapple can't actually intercept the active scan and go, yes, I am your network, I am here. Even if it's just a bogus fake network. So that is definitely a concern that we need to be aware of. That just means there are security concerns with wireless that you need to be aware of. That's really the basics for that. The 802.11 standard does define 4 main topologies called service sets. That's essentially how the wireless networks will connect to one another. We have a basic service, BSS, extended service, ESS, an independent basic service, and a mesh basic service. So we're going to have to run through these. Basically, the BSS is more of a closed loop where that's what it's there for. Then we have our ESS, which is more of an extended. So this is more cells. So basically the access points will be limit the devices. They will cover the main cell. In many organizational networks, it's very large. Not only a single access point can cover everything, so we have our ESS. So this is combining multiple access points to act as one. That way, users can walk from one access point to another more seamlessly. Then we have our IBS, and that's more of an independent, no centralized device necessarily. Device can talk directly to device. And those were the big ones. So what about MBSS, the Mesh Basic Service? If BSS, ESS, IBSS are the main ones, what about MBSS? Well, this is for more of a large city, so this is not for a small network. So when we're talking a wireless LAN, MBSS, it's there. It's going to be an extension of our extended service sets, but think more citywide. It's just a little bit more in depth than our ESS. But again, geographical area is a much larger space. So let's get more into our standards. So our basic 802.11 standards are more for our wireless, main wireless data networks. They outline the guidelines, the protocols, the controls, the operations for our wireless LANs. The protocol revisions were noted by the letter after the IEEE designation. So 802.11, that's the IEEE designation. 802.11a, b, g, n, ax, a, e, an, all of the other variations are denoted after the 802.11 something. Now again, you cannot just say 802.1 or 802.15. They're all different designations. Our wired Ethernet networks are 802.3. Our wireless networks are 802.11. The difference between them are the structure at layer 2 and some other fundamental issues. Well, Ethernet's typically wired, where wireless is going to be just that wireless component. But again, it outlines the structure that these protocols are going to be using. Several of them will have revision specifics on frequencies, channels, modulation, and things like that. Router manufacturers will use the letter to designate the different products to ensure capability. That way, if you're looking at a wireless network from 2003, realistically, you're probably doing 802.11g, but there is a actual structure for that. The actual structure shows Wi-Fi 1, 2, 3, 4, 5, 6, and it's not listed but 7. So 802.11g is Wi-Fi 3, and that was done in 2003. It used the 2.4 gigahertz, and that allowed for speeds up to 54 megabits per second. Then in 2009, so about every 6 years, we get another new protocol. So in 2009, we got Wi-Fi 4 with 802.11n. In 2014, we got AC. In 2019, we have Wi-Fi 6 with 802.11ax. And then now we have Wi-Fi 7 in 2024. So there are changes to these wireless networks to increase its operational distance, its speed, and the frequencies that they can use. Notice most of these are using 2.4 and or 5 gigahertz. With newer wireless standards, we're now able to take advantage of the 6 gigahertz range, hence the Wi-Fi 7 standard. What's really interesting is, in reality, after 2019 with Wi-Fi 6, we got a new standard called Wi-Fi 6E. Again, this is where they added the third band of 6 gigahertz. Not quite new enough to call it 7, but new enough to make a modification. It's like your cell phone, 4G, 3G, 5G. But then there's LTE, which came between 4G and 5G. There's always these little nuances. So the E stands for enhanced, and it is more available spectrum using the 12 megahertz in the 6 gigahertz band to work over, so you'll be able to support more channels without having to share any additional part of the spectrum. The potential for Wi-Fi 6E is tremendous, but does require buying new wireless equipment, smart TVs, smart appliances, and so forth. So to get the new advantages of new wireless network, you have to get new hardware, and you have to have the new infrastructure to support said wireless. So again, as we grow with these understandings of these different frequencies and different bands, recognize that the FCC controls them and regulates them. So here we have unlicensed bands. Again, all unlicensed bands, users can operate without the appropriate license. So they are not required to have a license when using the open or unlicensed bands. Narrow bands and spread spectrum bands do exist. They'll use little bandwidth by transmitting over a narrow beam for a frequency. For example, a 2 megahertz wide channel at 80 watts. So you're not using a large wide frequency, you're using a smaller frequency but pumping up the power. With the spread spectrum, the transmission is spread across the entire frequency space available. So you might be doing a 22 megahertz band channel, and instead of just using a small portion of that, you're going to use the entire thing, but you may do a little bit less power. You also have the ability to do multipaths, and that's where a radio wave will reflect off certain materials, sometimes, again, metals, people, water. This will result in multiple versions of the same radio wave bouncing around, and that's known as that multipath. Again, the multipath is multiple radio waves that originated from the same source, but because of colliding with other materials, there's now multiple copies of the original signal. We have the ability to do like a direct wave, and we beam it off of a building that reflects it back to a receiver. That would be an example of a multipath. We also said that some of them are dealing with different access to how they put the data on the spectrum. So here's two examples: frequency hopping spread spectrum and direct sequence spread spectrum. This is basically the multiplexing of the wireless signal on the wire. It works by, we're going to do FHSS first, and it works by transmitting data using a small carrier space in short bursts, then continuously changing or hopping to other frequencies during the transmission. That way, if there is a congestion on a specific frequency or band, you should be able to avoid it by jumping over the different bands. With direct sequence spread spectrum, DSSS, you're using hopping stays on a fixed channel, hopping within the frequency space on that channel, within the band that it has. This is done by using a technique called data encoding. Alright, so let's dig deeper in that access point. The access point is just what we think it is. It is a centralized device that allows for transmission and receiving of wireless frequencies. Again, a half duplex switch will contain a radio card and the antenna to turn it into a access point. It will be operating under the unlicensed frequencies, 2.4 or 5 gigahertz. The WAPs can operate on several different channels to increase its efficiency and to increase its frequencies. Again, channels 1, 6, and 11. So on the top, let me grab my pen. In the US, these are the big three. If we're using 802.11g, for example, it's still 1, 6, and 11. And then you're going to notice These are all 20 megahertz roundabout. This is 22 megahertz. This is 20 megahertz. Well, this is a 40 megahertz. And you're going to notice with subcarriers. And so they're able to operate just on channel 1. So that is definitely a newer improvement from previous wireless modules. The WAP will act as a portal for others' networks. Again, physical topology to a wireless. It will use radio frequencies to carry the band frequencies. Again, using the 802.11 standard, it will use the unlicensed 2.4 and 5 gigahertz range, and with the new variation of it, also our 6 gigahertz range as well. The access point will have radio cards that are configured to work with one another, normally 2 or 3 other wireless bands as well. It will continuously transmit beacons so that the clients can receive and then connect to those beacons. And the clients will have to use either a passive or active technique to find the beacon so they can grab information like the SSID and maybe authentication protocols to connect to that wireless network. Here we have our traditional 802.11 variation with WPA2. So, WAP client. We have an announce, and the client will receive it, will process the key, and will send back the SNOUNCE and a MIC back to the access point. The access point will now take that and include its key and will return both a GTK, golden ticket, and a MIC back to the client. The client, if allowing, will acknowledge and then associate itself with that access point. And that is true for WPA2. So this is assuming that the access point is actually working with that level of protection. There are different ways for access points to operate. Autonomously, being able to operate at the control and data layer, this will allow the access point to be more like a switch intelligence, where we also have thin access points, which will switch-like intelligence is stripped out and located on the controller itself. Wireless networks will also typically have a wireless controller, whether it's software or hardware on the network, but that device, that controller, will control a lot of the settings for the wireless network. So again, the switch-like software with thin access point is removed off the access point and put back on that hardware, providing a controller, that's the hardware, to act for the central administration of that access point. While this is a little bit more easier to manage, especially when we have multiple access points, there are some security concerns when actually having that centralized individual component to control access. But we have other devices out there, like a wireless bridge, for example. The bridge will be more of a distributed system that will translate traffic between the 802.11 device and the distribution medium used for the backhaul, like a wired connection. So we might have this wireless bridge connecting to a wired network so that they can translate between 802.3 and 802.11. If the backhaul medium is also wireless, then the wireless access point can also serve as the wireless bridge. 802.11 standards will describe the mechanism for the distribution of wireless systems, whereby the frame format can handle 4 different MAC addresses that could be associated with them. So normally when you're looking at an 802.11 frame, you can see 4 MAC addresses. That's part of the wireless distribution systems, or WDS. In the real world, however, deployments for WDS are in bridges, repeaters, and other mesh-based networks. So often used when there are several non-wireless devices, such as wired PCs, needed to provide resilience in the event of failure of a wireless network, and performance can be quite bad, but without the use of a wireless bridge, some devices would have no connections at all. So these are some common things for our network. Our residential gateway, basically if we're talking about home access. Home wireless routers will act as the gateway to their internet, whether it's DSL or cable broadband. We're going to have a all-in-one or SOHO type router. They typically will have a built-in hub supported for Ethernet connections and a built-in wireless access point for a wireless network. Again, our SOHOs are a router, switch, and wireless access point all rolled into one. They will provide the internet connectivity to various types of devices, but you are limited on what features that they do have. For the BYOD, bring your own device access, users often take advantage of the following major things: implementing encryption, setting limits for the transmission power, and setting the appropriate access controls for different devices. For the enterprise gateway, we're going to have a dedicated router, a dedicated switch, and dedicated access points. These will actually use integrated hardware, and that way we can have enterprise-grade equipment and resources. The enterprise gateway will also have a wireless LAN and controller and a wireless LAN controller, enabling it to act as a translation bridge between the two types of medias. Typically deployed as a guest point of access to the internet with no direct access to the corporate network. You can have multiple. So what exactly does that mean? If we have a gateway, we might have a wireless device that might be tied to the guest, and we might have our switches that will connect to our enterprise wireless networks. It really just kind of depends. And you're noticing I'm drawing antennas. That's because in our access points, the antennas do matter. Not all antennas are created equal. Some antennas are omnidirectional, meaning full 3 coverage access. Some are semi-directional, and that means they're kind of 180. Some are directional, and that's more coned off to go to one kind of direction, whether it's a 45 or 90 degree. Let's go and draw that out. So if we have an antenna, we might beam it in one area, directing its path, or we might do a much wider, or we might do a access point, and that's going to be a semi-directional, or we can just do a full 360 if the access point's in the middle. And so there's different types of antennas. Here we have an example of a Yagi antenna that's going to be more directional. Here we have a planar antenna. This is going to be more omnidirectional. We have a highly directional or more very specific one. Again, that's going to be more of a point-to-point. That's going to be the more narrowly focused one. And this will also be using more of a grid antenna or a parabolic antenna. Here's an example of a grid antenna. Again, this is more focused and more directional. Here's a parabolic antenna. Again, more focused. This allows for communication to go a little further as opposed to allowing transmission to be semi-directional or omnidirectional. This can put all the power in a more narrowly focused beam so it can go a little further. What gets interesting is people think we're limited to one antenna, and that's not true. We also have what's called a MIMO antenna, multi-input, multi-output antennas. And this is definitely a much newer technology, very keen on 3, 4, and 5G or LTE for cellular, but it's also included in anything above 802.11n. Again, with MIMO technology, this will allow complex signal processing techniques to provide better range, throughput, reliability, and resilience to wireless noise. Here's an example of a Wi-Fi router with MIMO antennas. Again, sometimes you don't get to really see the antennas. They're all internal, so that's something to definitely take a point of. So to determine the appropriate coverage range, you need to do a few things. First, look at the antennas. It's important to understand the antenna coverage from the different vendors. So you will have to look at what antenna from a specific vendor that you're going to be using to kind of gauge your coverage area. That kind of sounds like a site survey. It really is, and we're going to get into that in just a few slides, but I did want to point out that there are structures for that. So again, the charts that are going to look at the antenna coverage, that's a planar chart or a radiation envelope from the different vendors. Each antenna type will have specific characteristics, so you need to understand that and how it relates to your environment. Shown in a coverage chart, there are two perspectives: heads down, or a horizontal aspect, or a side evaluation and a vertical aspect. So here's a perfect example of a horizontal and vertical. Top down versus side. Here's our E plane and H plane for, this is a semi-directional coverage map, so you can kind of see where your coverage is going to be. Again, all of this goes back into planning your coverage for your environment, and we call that a site survey. And the site surveys are used to determine the radiation and how it will behave within a facility, i.e., how your frequencies are going to work in your environment. It will take into account the coverage, interference, gaps, placement of equipment, power consideration, and all of that, as well as noise. So again, I know I said interference, but again, it's really important to stress that noise component. The site survey process varies greatly in its complexity based off of the person that's doing it and kind of based off of your needs. Should include the capability for planning and identifying possible areas of interference and noise so that you can better figure out antennas or coverage areas for the areas that might have additional noise. The spectrum analysis will allow us to help to detect the frequencies, the interferences that might cause additional damage or additional noise to our wireless networks. Using a spectrum analyzer, we'll test a device that will measure the amplitude and frequencies of radio waves. The spectrum analysis will enable you to visually map the activities that are already existing on your unlicensed spectrums or bands. Again, the 2.4 and 5 gigahertz bands. If background noise is excessive, normally will exceed 85 decibels, the wireless network will not work correctly. Anything really above like 60 decibels, we really have to be more careful with. Anything above 85, again, lots of noise. So what makes noise? Microwave ovens, cell phones, your neighbors, transmit jammers, motors, fluorescent light bulbs, other transmitters. So there's a lot of things that actually can interfere with your traditional 802.11 items. If you're using just 2.4 gigahertz, your microwave, your cordless phone, all of those things interfere. Now, if you're dealing with 5 gigahertz, then your cordless phone typically won't be operating in the same frequencies. But again, you have to look at more common networks. The coverage analysis, again, you will conduct a site survey to map out your coverage area. And that will also be in the capacity planning. You basically collect information and you will establish the capacity and coverage requirements based off of the density that is necessary for your signaling for your environment. No specific tools are required other than a signal strength indicator. You can get that from a laptop or a smartphone. That can show you the coverage areas. That will allow you to look at your access point placement. Remember that there are coverage limitations, meaning you can only be about 100 meters away from a switch with a wired connection. And again, you'd have to kind of look into your physical limitations on where you can mount equipment. The site survey will dictate the location and the boundaries, but you might also want to look at your gaps, and if you are really close to an exit, maybe lowering the power. Again, mixture of antenna types in here as well. Omnidirectional more centralized, where semi-directional more for exterior. Again, you're going to play with it to find the best layout for your environments. Coverage assessment, again, looking at a site survey, after all the access points are in place and allowed, operational, and verified, you're going to check. You can do your methods by a passive mode or an active mode. Basically, a client card is used to collect the appropriate measurements and signals, and you can check the measurements. Or an active mode, that's a client will authenticate and associate with access points working at the main three layers, layers 1, 2, and 3. There's a predictive method as well, which will use a predictive modeling application and simulation software to create your visual modeling for the RF coverage. That's way more in-depth, that's way more expensive, but definitely is an option if you're doing this more professionally. You also have the ability to self-organize wireless networks based off of newer controllers. The newer controller-based access points provide the ability to dynamically reconfigure itself, and the lightweight access points based on changing RF conditions. Again, much newer technology, but the wireless networks can kind of self-manage and self-repair based off of the noise that is occurring on the network. Alright, that is it for this module. We covered topologies, spectrums, standards, hardware, anatomy, antennas, and all the variations of site surveys. Any questions or concerns, definitely feel free to reach out. Thank you. Alright, that concludes this lecture review. Again, all of this material is copyrighted by JB Learning. I was just providing video lecture on their official PowerPoints. Questions or concerns, definitely feel free to reach out to me. I'll answer them the best that I can. Thank you for listening to this lecture review.